Okay. What are we talking about today? Okay, so today we hello people, sorry. I really apologize, yeah. Okay, so today we are going to talk more about these fundamental things that I've been laying out. Emergence, we're going to listen to Steve Strogatz talk about Emergence and a couple other characters who are connected with the Complex System Center in various different ways. Josh Bongard has links to these people. It's going back maybe 8 or 9 years now, but it remains a very well put together part by its Radiolab on the limits of our understanding. And this will remain. It's unclear how much we'll be able to figure out about everything in the universe and so on. Can we just simulate things? That's pretty good, but can we actually deeply understand them? Like we've had tremendous success, and maybe that stops. Maybe that we run out of time. So that will be the sort of Strogatz point of view. I want to put Pratchett up because I think we need some happiness. And he's doing well. This is the ridiculous. He doesn't read the news, right? So this is the please pat me business. It's unbelievable. This should be purring. Can you hear that? Anyway, he's a great cat. He's just a winner. Okay. Ridiculous cat. Okay. This is the whole world is my bed. Okay, right. Great cat. And here he's just asleep. He's just simply asleep. This is just professional sleeping. All right, so I feel we need to do that. Oh, this is good. This one got some likes. Yeah, victory. Just general victory there. Okay, all right, so let's go to some other things. So actually this Hedonometer thing that we have, and we've had this version of this website. We had sort of a clunky one to start with, and if you go up to Farrell, you'll see there's a long picture that's attached to that thing you can fall into, whatever it is that. I'm afraid of heights, so it worries me. But and that's made with MATLAB, right? That's a MATLAB script, right? So years ago, I would build all these things with MATLAB. So Andy Reagan put this one together. We worked very hard together to make all this work, and I know I've shown it too. But anyway, so we tweeted about this on Monday, on Tuesday, I guess, because that's when we had the data in. It's a terrible thing. You can see that it actually, in terms of the history of all these things, this is actually some memory. Like there were a couple of days where it was really being talked about so much that it pushed the dial down. It's kind of back up, but if you look at the words now, so there are still these negative things, but shooting has gone down relatively, right? So a lot of this terrorist, those words have actually disappeared. Tax is still falling off the list. So this is this thing we're trying to get to. What are the stories that are actually being talked about? And you get a glimpse of where the narrative has gone, right? It's moved away from, say, terrorist. And actually about victims, and I'm not, and partly this is because 2 days before there was just so much. This is compared to the 7 days before, right? You have to compare it to some other texts. Compared to the 7 days before, so that's part of it. Anyway, so this guy, Reuters wrote about it. It's in the New York Times. Ariana Huffington tweeted about it. Like one of those things. It got a lot of stuff, and the followers keep going up on the little Hedonometer Twitter feed, which is here. So we're kind of. I mean, it's a terrible thing. This is the Reuters article. It's a terrible thing. But we've wanted to make this. Well, we've had success with it, but we want it to be a part of the social dashboard, right? And we've actually created some dashboards for other countries. So, we'll see how things go going forward. So it's not about necessarily the bad things, but trying to understand. So this is what I was going to mention actually. If for projects, if anyone's interested, and I know this is a bit of a funny thing, but this is still somewhat not completely understood by us. There's a lot of demographic change, right, in who's actually using Twitter, and that's a difficult thing to quantify. But that dip there, and then this sort of steady decrease since January 2016, right? So it's been kind of going down. It seems to be. There are periods here, because I'm the one who annotates this, there are periods where not that much happens, right? You don't have to annotate much, right? There just aren't that many events, but it has just been, Barney Bananas in the last couple of years. It's just things, and you have to mark them. So it looks like that, right? And I feel like it really does look like, but it's tough. So early on, and I should do it on the, early on, very relatively few people are here, on Twitter, right? This is early on. I mean, it's known about, it's people are using it. So there's really a change, there's a change in the usage, or the number of languages that are on and the fraction the languages have. That really grows over this period. So you'd have to get in there and see if that's true. We've done some basic stuff in it. There's a lot more swearing, actually. Swearing is very prevalent on Twitter, and it's actually quite, a useful thing to measure, just like ha 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 is as well. So the Portuguese, Brazilian Portuguese, they put KKKKK. That's it's like ha ha ha, but it's much easier to type because you just hold down the K. So you get a different statistic for that one. Most languages have, like Spanish is JA, 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 JA. Korean actually has, you can put pies together, and that's like anime sad face, right? Like crying. So you can actually kind of have the antiparticle for ha ha ha. They have the, right? Because in English you don't really do that, right? We're more with emojis now. People put sad emojis to indicate the strength of their sadness. But this has been going down, generally it's pretty robust. And there's also in here, there's variance is not being shown, right? So there's variance, this is just the average for each day. So there's variance, there's the second level. You can get down to the second level. We have the data for it. It's in big boxes of 15 minutes of tweets, which we have backed up a lot. It could go horribly wrong. Anyway, so that one took off. We will talk, of course, I've promised that we will talk about success and how things take off. And what is that? Oh, it's an ad. Okay, so it's happiness for some people. So we tweeted a few things out. I said, Hedonometer tweeted, and so this is Danforth's tweet, right? It's got 1,700 retweets now, which is solid. The best one from our immediate group is from Jim Bagro, who took a picture of cabling at the VAC, at the Advanced Computing Core. It was all very well structured and put together, and said something like, someone says you can't photograph happiness, but it's not true. Here it is. It's just like a sort of and he got 10,000 retweets. People loved it. Anyway, you don't know what's going to take off. We'll get to that. All right. Okay, so. Have we all forgotten about this? No, but it's definitely not enduring, for weeks. And it depends what people say. So Charlottesville very much had that, right? There were a couple of days. And then it really was about Trump sort of going back and forth on some things that he said that made it keep going. And then we got into a Barcelona terrorist attack. So messaging. Okay. We've talked about the cat. That was important. Okay, I think we can go on. What is going on? All right. Okay. Volume? Okay. I've actually been unwell for 2 weeks, so I don't know what's going on. Anyway, so up and down. All right, so I could run out of pulmonary oomph. Okay, so we went through this, and maybe you guys played around with this. There's a whole website that she has with tons of other examples. And they're very much in the vein of these simple toy models, that some of which have been around for a very long time. The Schelling's model is extremely famous. And it actually continues to be studied as a model, but in terms of the story it tells, pretty powerful. Okay, so he thought about a lot of these little things, like people are making decisions in simple ways. All right, so I had a couple of other examples of emergence. I feel like this one has endured and will stay there. It's taste, right? So the taste of food. People really like food, right? We really like food. Instagram, let's take pictures of our food. And then we get upset about it. But nutrition, I think, is still, the science of nutrition is still in this kind of weird thing where we are at the level of, let's break it down into the elements, right? It's like saying, here's my friend has got this many carbon atoms and this many hydrogen, and here's a little bar chart for the atoms in them, and quarks maybe, if you want to get really detailed, and you say, that's what they're like, right? And that's not, I think you'll enjoy them. you'll enjoy meeting them. You know, that doesn't work on Match.com or whatever it is. Okay, Cupid. Wow, bad stuff. Oh, so, but we are still there, right? I mean, that's what, you know, we've got this point where we have it on the side, the fats and the carbohydrates and all these things. Yeah, yeah. So this is pollen, who's a bit of a hero here, but somehow taste emerges, and that's kind of a complicated thing, and also, you know, whether it's healthy or not, right? So he talks about reductionism here, which is just a natural part of science, but we're a long way from, you know, a really advanced version of nutrition, although we're getting to a big data part of it, I suppose. Actually, there's, well, I'll show, maybe get to that later. There's some great studies now of online recipes, and I know I showed you a little bit of this for power law size distributions for the number of recipes things are in, but you can get bipartite affiliation graphs of, so you can end up with the foods here and the ingredients here, and you can start to see them split apart, right, into sort of savory and sweet, for example, and see that they're different cultures. Anyway, so, you know, I mean, biology, right, this is a very complicated thing. So we break it down into components. We've got to do that, right, but the whole may be more than or just different from. It's all these words, the sum of its parts, right? It's a reductionist science thing. So this is a long, I mean, it's 2007, it's a long article. It's worth reading, I think. I don't know if I have it here, but he ended up with this sort of distilled thing. What was it? Eat food, mostly plants, not too much. That's it. Okay, so my mother's actually a home eco teacher. That's her career, and needlecraft. So we three boys learnt how to do all these things. And she would always talk very simply about food. Food is fuel, right? So we got the whole food. This is on a farm, you know. Food is fuel. This is what you're eating it for. Shut up, you know. So I have a fairly plain sense of things. Anyway, so lots of things. So fruits and veggies, right? Prevent cancer, and you know, there's the too much meat stuff, right? That was a finding a while back. There was a clever thing done with that because it was like, there's too much meat, but then it's saturated fat, right? So we went to the constituent thing. Like it's not the whole, it's this part, and then coconut milk is no good, right? Right? So it's true though, people said, oh, the saturated fat, that became a big, big deal. And in fact, you know, that is that's been a disaster. We've had 30 years of saying fat is no good, and the fat-free ice cream, which is laden with sugar, and it's a very sort of simplistic idea that if you eat fat, you become fat. But you know, we do things with sugar because bodies, right? Anyway, yeah.
Well, it's the whole sugar, all that, you know, all those questionable studies paid for by the sugar industry.
Right, big sugar. Yeah. Yeah.
Also salt as well.
Yeah.
Apparently they tried to pin a lot of that on salt.
Salt was the strokes, right. Right, and they point to Japan, you know, and these sorts of things. Yeah, salt's a disaster, yeah, except it makes everything taste good. I remember visiting a friend who was from Milan he's talking to us while he's trying to make the pasta, and he's just like, with the salt into the water, and we're just like, maybe we should stop. But it went on for like a minute as far as it did. Unbelievable. Did taste good. So, but yeah, salt, basically salt, butter, and sugar, you can make anything taste good. Yeah, which is how restaurants work, yeah. So, there's some food in there. You know, and all the early, like the Moosewood vegetarian cookbook was a big deal for vegetarians, you know, back in the day. If you look at how that one works, right, it's like, make the thing and then just cover it in cheese. Like that was the end, and maybe paprika. And that was like the end of every recipe, to like, save the world. But it was pretty enjoyable. It's like, I think I understand how you do this. Okay, people like cheese. Right, so find the nutrients and then you eat more of them, and of course now we have vitamins and multivitamins, and then long-term studies start to suggest if you take multivitamins, that's not good for you, it's bad, yep. Although I'm pro-zinc, I had a zinc thing recently. And then it turns out, right, carrots, eat your carrots so you can see in the dark, beta-carotene, too much, right, because now you start eating unbelievable amounts, it can go the other way, right? So then you have, and so this is from this article, again. Time, right? So we like our things, you know, so time. There are lots of things, so we're smart, we know all these things are in there, but this is not what you would want to present to someone on a menu, or, and we know it tastes good, and we've known that for thousands of years, and that's sort of the story here, right? Meantime, we can enjoy, right, the knowledge probably doesn't do any harm. We've figured out, A lot of people have died basically to show you which mushrooms you should eat and shouldn't, for example. Not great, but it's true. We've had a lot of a big experiment going along. So people have been here forever. We like, yeah. I mean, you might say the same thing about Big Macs, but yeah. So this is actually kind of a shelling story again, the theory and practice, right? And I've said this before. Baseball, like throwing baseballs, remains somewhat of a mystery. People still can try to simulate it and try to figure out things because of the strange fluid dynamics there. Bumblebees, famously, fluid mechanics people said that thing cannot fly. It is not, there's something wrong, right? It must have a motor inside it or something, because it just made no sense, like, the calculations. Anyway, and apparently they produced some very weird little turbulent things that help them, right? You have to get a bumblebee in some little chamber with some colorings and so on and get it to fly. Presumably by feeding it or something. But, this is a really difficult thing for us, right? We want to understand these simple models, and I have more coming up, these, like shelling and so on, these simple models, and even in fluids, where we have the equations, right? We actually have the equations. We do really well with some simple parts, and then we have to just go right out to the other end with computational stuff. And that's a concern, and that's a real concern for modeling socio-technical systems, how people move around, all these things. Are we doing a good job, right? Lots of crazy assumptions in those big models. Oh, this was a thing I sort of put together well. Yeah, collateralized debt obligation, right? Tastes good, but it's not, the bits inside aren't so great. So, but it's got an A rating, and it's made out of junk pieces, yeah. And you sell it to Germans who are trying to invest in your country. Right, so 2008 is the house, yeah, is that what it is? Yeah. Things go boom, it's a big surprise. Economists don't know. Yeah. Right, in terms of predicting systems, unbelievable, right? So some people did, but some people will always get things right if you have enough people because they're crazy, right? But but there is that mystery, The Big Short by Michael Lewis traces a couple of those characters. And essentially it's sort of a detective story for them because they're like, this smells bad, this is, they look inside the hot dog and they're like, what's going on? And then they have to go and look at a lot of other hot dogs and they're like, this isn't good. This is good, you should not be eating this. Anyway, this is a line from a poet. Made of stories, not of atoms. I'm quite partial to this. For TV fans, this is quoted by Metatron in Supernatural. Great show. Although everyone seems to die except the two main guys. I ride my bike in the basement and I have to watch things. Okay, so narrative. So Pratchett, my man Pratchett, the cat is named after this guy. So narrativium. So he has this ridiculous world, which is fantastic. So it's the most common element, right? Not included in the list of 5: earth, fire, air, water, and surprise, which is a terrible pun. Element of surprise. Right? I'm sorry. We have to get that out of the way. It's really awful. But a little narrativium goes a long way, and we'll get to this with Star Wars, of all things. The simpler the story, the better you understand it. This is a big deal, right? And this is why we don't understand the stories of a collective. That's why the shelling model, for example, is very powerful for us, because we get a little story that we wouldn't have guessed as individuals running around. And 26 letters and some rules of grammar are no story at all. Right. There are other kinds, I've talked a lot about this like micro to macro thing, and we have this great example of Simon's model, and we'll have some others coming along, but fluid mechanics again, right? Lots of little interactions gives rise to some bigger behavior, how people interact with each other locally. But you can have much more complicated things where there are many interactions across scales, and that definitely is, it's much harder analytically, and it's the sort of stuff that possibly you can only really simulate. Machine learning type things explode and right, trying to model how we think, for example, or play Go, they can do well because they really do have built into them, deep learning it does specifically, like this across scale stuff. But even mathematics, this is a just ridiculous thing. Gödel, who was totally nuts, right, and was scared everyone was trying to poison him, but he eventually showed that, there are theorems that you can't prove that they're true or not, right? That's a really, and then everyone said, okay, and then just kept going, because that would be really awful. I mean, that's sort of the distilled version. But but this does sort of in a hard way. So there's a strong form of emergence, right? That we may not actually be able to, start with a simple model with simple things we understand and we can kind of explain to each other, let it run, and then kind of watch how it all pieces together and get the system story. There may, and if we do the right thing scientifically, we'll be able to say these are things we just can't understand, right? They're really, and here's a mathematical reason for why, just like Gödel's theorem, we can't get that far. This is a little more philosophical, I suppose, but and there's this idea of weak emergence where, like Simon's model, where we can kind of go through and we can derive it all. Fluid mechanics is the same thing, big deal. Strong emergence, where we can't really deduce it. So reductionist techniques are absolutely essential, right? You have to figure out the individual bits and how they interact with each other. I mean, this is what social psychology does all the time, right? How do humans interact with each other? And it's full of madness and so on, but that's the game there. That's the problem with strong emergence. Anyway, but it could be, and this has certainly been the way things have worked over now thousands of years, that we haven't got the real mechanism out. So we're not really sure. So there's this boundary of knowledge that we keep pushing out, right? Where we're like, oh, now we can explain that one, and now we can explain that one. But we may get to an edge where the stuff beyond it, and we can define that edge, we can say this is the edge, that stuff out there, we can simulate it, but we can't, there isn't a simple story. And so the brain is in that kind of box, right? The European Union has had some huge flagship things they've put together. There are 2, I think, every 10 years, something like that. And one of them is basically making a brain. That's what it boils down to. We're going to make, in 5 or 10 years, we're going to make a thing that behaves like a brain. So good luck. But who knows? I mean, things have really accelerated recently. But that's going to take a while. Positronic brains would be the Asimov thing. Okay. Black boxes. So we'll get to this. This has, of course, become more and more of a story for people in general because of the rise of algorithms in people's lives and not knowing how they work, right? Not knowing there is an algorithm there. I mean, there are things like sentencing now for, in criminal courts, right? You put in some data about the person and push a button, and it gives you some probability of recidivism. I said it wrong. Recidivism, or what's right? And this is some black box. It's proprietary. You can't see. It doesn't give you a reason why. So a lot of, obviously people are upset about this, but companies as well who want to serve people in a better way and are good, trying to be good entities, are trying to figure out how they can do that, right? And so Josh Bongard's got some long-term work in this, and we'll come to that in a little bit. Can you model the thing, but also get out a little story to say, this is why it's happening, right? This is what's going on. We've been very happy with being able to just reproduce something because that is a huge achievement. You put down a neural network and get it to make reproduce the behavior you see. That's a real achievement, and you can do things with that. But we really want to understand things. So this is what this is, and hopefully this will work okay. So, I should do that. So let me just try to set this up. We can do slow TV. So this is.
You have to be crazy. You have to be crazy to spend 65 hours.
I have
making
no idea
a
what that
suit.
is. Oh, it's over here. It's an ad
layers
for
of steel to create one knife. Or to make whiskey by malting your own barley, crafting your own barrels,
so, right,
and
so I
applying
have,
a malt master who's been.
Right? That's what you want. So this is the problem. It can go wrong. I used to have 30, but they only like. Okay, so virtual desktops, people. It's cool. Yeah, let's just put that up so we have something to watch. And we need to mute that one. Let's do that. Okay, now we can release this again. Okay, but let me just talk a little bit about this. So I've talked about Radiolab a little bit. And in the past they've had some really tremendous episodes. They kind of go up and down. That's just my opinion. Maybe I mentioned this to, I don't know if I said this class. We're going to talk about the small world search problem, how people collectively can find things, and this is work that stretches now over 50 years. It's a big deal for organizations, for finding knowledge and all sorts of things. Even say finding the Boston bombing characters, right? That's sort of the most wanted thing. It's a collective stuff where you're somehow engaging many people to find something. So it can be for good and bad. There'll be something about red balloons, which is a bit strange. So they had an article. They had a piece. I don't know if anyone of you heard this, but they had a pretty dangerous thing where they talked about 4chan. Like I'm worried I'm mentioning 4chan. And it was with Shia LaBeouf. I mean, this is really strange, right? And so Shia LaBeouf, so when Trump got elected, and I guess it's on his inauguration day, he set up this thing at some museum in Brooklyn where people could come and stand in front. I mean, it's really goofy, right? And stand in front of a camera, which was live streaming the whole time, and say something like, he will not divide us, which is a very important thing, right? He will not divide us. Okay, so that's the framing. So people are doing that, but within about 4 hours, it's sort of spread around this thing exists, and the 4chan people are out there, and they have, they find it, and they start to, ridicule it and mock him and so on. And so it all goes to pieces, and he gets arrested for actually hitting someone. It's just a disaster. But the thing about this is it's the small world search problem we'll get to later on, because he moves it to Phoenix, I think, or Albuquerque, and they find it again, and he's like kind of goading them. And then he just replaces the whole thing with a flag. So there's just a flag. You see the flag go up, and there's just blue sky behind it. So this becomes the hard search problem, right? And just says, and sort of looks in the camera and says, whatever. And they find it by sundown because they track it with plane flights. There's planes going overhead, and they're listening to frog sounds and all sorts of stuff. And eventually someone, they figure out because of these trails that, it's like a TV show, that it's going to be somewhere in Tennessee. And one of them, who's nearby, gets out in the truck and starts driving around and beeps a horn. And they're like, yes, you're getting closer. It's unbelievable. And then they get in there and they wait till night or whatever, and they go in and take the flag down and put up a little MAGA hat and shirt or something and say rude things into the... Anyway, it's surprising how fast people can find things if they're motivated. And they were motivated by him being him. They took that down, right? They took that down. It was up for about a day, and they're like, oh. Because they got a lot of, I guess they didn't say, I don't know. Their normal listeners wrote in a lot of bad things. So they've had, Radiolab goes up and down. I just want to say that, and it sort of ties a little bit. I know, I'm talking too much. Anyway, this piece is limits. Really interesting. It's the limits of everything. And it starts off with Ironman Triathlon, actually. And it talks about, what's her name? Julie, anyone remember this if you know these things? Who crawled across the line sort of famously, and, right, like how do you get people to do these extreme things? And then it gets on to the memory, like our limits of memory. And there's a Russian guy who's very famous, who's just called M, and he used to stand on a stage and he'd have a whole audience and get them to talk for 10 minutes, and then he'd be able to say everything they said, right? I think apparently he read Dante's Inferno in Italian, he's Russian, in a cafe, didn't understand Italian, but could repeat it all. So he was basically just a complete recorder. And he had all this synesthetic stuff that would go on, like all these other stuff would kind of pop and go on, so he had all this extra tagging kind of going on. Eventually it did become problematic, like later in his life it became, because he was not making meaning, right? So part of healthy psychology is actually forgetting stuff, right? You need to process it and get rid of it. But he was this basic sort of a show, but it's only 2 or 3 pounds, and it runs on 30 watts or something, and somehow you could record an incredible amount of detail, right? So it goes through that. It talks about the guy who, I think Slovakian guy who won Ride Across America 5 times, which is an insane race, right? You're riding across America. It's very extreme. People get into all sorts of states, and he would predictably, after about 10 days, start to hallucinate. And they would, his crew allowed him, I think, to choose his own music, his speed. There were like 3 things he could choose. But he would start to think, and he was from the military, he started to think the Russians were coming, and they would say, yes, they are. And he would ride faster. Anyway, so he'd get off and try to fight mailboxes and stuff. Anyway, so it's a really interesting, it's about an hour, and it ends with this piece that I want to play with you. What's that? Yeah, she was tilting it at mailboxes, yeah.
I'm Jad Abumrad.
I'm sorry if it's too loud.
This is Radiolab. Hey, I'm Jad Abumrad.
I'm Robert Krulwich.
This is Radiolab, and this next segment began with a simple question.
Mm-hmm. Seeing as our topic so far has been limits, and we've done body.
And we did the brain.
Now we're going to go really big.
Yeah, so we called up Steve Strogatz, mathematician at Cornell University, frequent guest on the show, and we asked him,
are there limits to human knowledge?
Yeah. And his answer sent us on a little adventure.
Is there anything that's at the limits of our knowledge is a question that a lot of us scientists worry about. And certainly the 20th century taught us that there are many things that limit our knowledge. For instance, the Heisenberg uncertainty principle in quantum physics showed us that you can't know the position and momentum of a subatomic particle at the same time. You just can't do it. It's not a matter of not having good enough instruments or not being clever enough. It's just a fundamental barrier that nature puts in your way. In logic, Gödel's theorem tells us you can't prove certain things even though they're true. So there are all kinds of limits, but those seem a bit remote from everyday experience. And yet, I think there are really important limits on our knowledge that we're all familiar with. What I'm thinking of here is our inability to think about big numbers. Because with your fingers, you've got 10, normally. So we're good at 10. We're barely good at 100. And once you start getting to thousands, millions, billions, and trillions, it gets hazier and hazier. When you hear now about the trillions of dollars in the deficit or whatever it is, the debt, that means nothing. How are you supposed to think about that? Now, when you ask why can't we understand the common cold, but we can put a person on the moon, it has to do with large numbers.
Not just large numbers of numbers, says Steve, but large numbers of things interacting.
That there are so many genes involved and so many biochemical reactions involved. Our brains are limited. Our memories are very limited. And so I worry a little bit that we might be approaching the end of our ability to have insight into certain kinds of questions.
What Steve means by the word insight is not like he found the answer. It's like that.
It's like a feeling.
Right.
Like that, oh, I get it.
The feeling you get when you really understand the answer.
Yeah, that satisfying feeling that I can see the reasoning.
I can actually feel it in my bones.
That's a very pleasurable feeling, but one that we may not always be able to enjoy.
I mean, you can see the space. Good luck.
We weren't really quite sure how to feel about this, but then Steve said, don't take my word for it. Talk to these guys that work down the hall for me. You'll see.
Yeah, we can go right ahead.
Cool. Can you guys introduce yourself? Tell me who I'm talking to.
Yeah, so my name is Hod Lipson.
My name is Michael Schmidt. I'm a PhD student.
And I'm a roboticist.
And Hod and Mike have developed this thing, which does make you wonder if Steve's right. It's a computer.
Yes.
Actually, many.
A whole tower of computers that are all grinding away and performing calculations.
Actually, when you get down to it, it's just a piece of software, but they've named it
Eureka,
because that's what it was designed to do, to have Eureka moments.
Maybe a kind of simpler example.
And the story of Eureka begins pretty simply.
Let's think of
with a
regular pendulum, okay?
With a pendulum.
Just one of these things you see hanging off a grandfather clock.
Okay, I've got a regular pendulum swinging in my mind.
Okay, swinging left and right.
Now, says Hod, double it. Instead of a string connected to a ball, make it a string connected to a ball, connected to another string, connected to another ball.
which is basically like a double pendulum. The cool thing about this is you just put it up, you lift it up and let it go.
And what you'll get, says Mike, is
chaos. It's really crazy behavior.
Instead of nice and even, now you got random.
It's almost impossible to actually try to predict where this thing will move.
So what they did was they got a camera, connected it to Eureka, and basically just had Eureka watch this thing, move about crazily. And then they asked the computer a really simple question. Can you make some kind of sense out of this erratic behavior? Like, is there something in this system that always stays the same?
Tell me, what about these pendulums over time is not changing?
Because with everything, there's got to be some kind of logic in there. So you're looking for a law, basically. I mean, you're looking for the law of the double pendulum.
Yes, that's the idea.
So Eureka is there watching this pendulum.
It was about 3 a.m. in the lab.
And it's basically spitting out all of these different guesses.
It's formulating hypotheses.
It's getting closer. Closer.
And then onto the screen pops this simple formula. F equals M What is F equals ma? Is that actually the law that...
F equals ma is Newton's law of motion.
The Isaac Newton.
That's Sir Isaac to you.
It's a basic law of physics.
And one of the greatest discoveries in the history of human thinking.
Took it about a day, 24 hours. But the interesting thing is that it came up with this thing without knowing anything about physics, nothing. That's why we think that this algorithm might be able to find new laws that we don't know about yet.
In fact, once word got out about Eureka,
That's when the emails started.
A couple of emails a day.
From scientists all over the place who were like, hey,
you mind if we borrow your robot?
for what kinds of stuff?
Anything you can think of, from trying to predict behaviors of cows in a herd to particle physics to the stock market.
And this is when we get to Steve's point about the limits of insight.
That's when they met this guy.
My name is Gurul Soel
Gurul is a biologist.
at the University of Texas Southwestern Medical Center.
He got in touch with Hod.
When he said, I have this amazing data, which is single-cell dynamics.
Meaning he's got this tiny little thing,
It's a simple bacteria.
really basic,
And he's been collecting this information on how it works.
on its inside.
How things go up and down. Certain nutrients increase, certain nutrients decrease over time, just like a pendulum.
But the thing is, in a cell, it's like thousands of pendulums.
There's so many parts.
Genes turning on and off.
Thousands and thousands, tens of thousands.
Proteins turning on other genes, nutrients going up and down.
It's this crazy quilt of complicated feedback.
And he wanted to know, inside of this cell, how are all of these things related? I mean, we can measure it all. We can see things going up and down and all that.
But what are the rules?
What are the rules?
Yeah.
And this, he says, is the problem for biology.
Biology is one of the least well understood systems compared to, let's say, chemistry and physics.
They're still lacking the basics.
So we said, look, Mr. Robot, can you tell us what you think are sort of the important principles governing this organism and maybe detect things that were hidden from us?
So he sent us the data, and we analyzed it. And
Well, okay, let's
Yeah,
not
what
let... Yeah,
happened?
so what happens?
suddenly, equations starting popping out.
Almost immediately.
The robot came back to us and said, okay, here's a set of two equations that describe your data.
Do you remember by any chance what the actual equation was? Not that we'd understand it, but just sort of to hear it said out loud.
Yeah, no, I don't. I don't have my Rain Man skills developed to that degree yet.
The important thing is that the equation was telling him things like, when this protein goes up, this other thing always goes down. And when that thing goes down, this gene turns on and then does a loop-de-loop. And when he went to his cell to check all this out, the equation was right.
These equations matched the data. And in fact, they explain new data.
These equations could even predict what the cell was about to do. But, hold the champagne, there's just one little problem here. The formulas check out, but
We don't know what they mean.
you don't know what they mean.
Right.
Meaning they don't know why these equations work.
Why when this goes up, does that go down? Why when that goes up, does this go sideways? Why?
I had to first look at this and try to make sense of it. We said like, oh, okay, I think we understand. And we're like, oh, maybe we don't. We think that we're close to understanding it.
But, now we're in this bizarre situation. We can't even publish it right now because we can't just publish a equation without explaining it.
So in the end, they're in this awkward position where they've got the answer, but they don't have the insight.
And I think it's a preview of what's to come in science.
The more we turn to computers with these big questions, the more they'll give us answers that we just don't understand.
We'll be faced with this challenge of having to find ways to get a computer to explain what it found.
But that will leave us, if this really happens, in some weird position as bystanders where we're sort of listening to the oracle, but not really understanding the answer. Is there going to be a time when we can't cut it anymore? We've had this window in human history when we could not just know things, but actually understand them. That is, you could know why they were true, not just know, but to know why. And that's a beautiful moment in human history, but I feel like it may only be a moment.
Well, I don't really see it quite that sort of sad and dramatic. Because at the end, there will be simple principles to describe even the most complicated of processes.
So you have a bias that prevents you from feeling the kind of despair that Steve feels and that we were hoping you would feel.
Oh, well, I have a positive outlook.
Well, I'm just wondering about the we. Look what we have discovered, you'll say when you're an old man with your robot sitting there in a dress next to you. And the robot will be holding your hand, but that will be a cold hand. And Jad and I will be thinking, I don't know, who's the we here?
Well, I would say we is sort of knowledge. I'm just thirsty for understanding and thirsty for knowledge. Me and the cold hand holding my hand, we've accumulated and contributed to the overall understanding of something that we thought maybe 50 years ago wasn't possible. And that would be something that would make me happy.
Hi, this is Steve Strogat.
So that's at
Radiolab
the
is produced
advent
by
of
Jad
deep learning.
Abumrad.
2007,
Our staff
that's when
includes
the
Alan Horn,
first paper
Michael
was
Raphael,
published.
Soren Wheeler,
If I've got that
Lulu
right.
Miller, and Pat Walters, with help
so,
from
that
Adi
was,
Narayan, Tim Howard, and Sharon
that made
Shadid.
this kind of problem even
Special
more
thanks to Stephen
clear,
Auerbach.
right? Because suddenly
All right,
we could
thank you.
model
Bye-bye.
all sorts of things and understand
End
them
of
even
mailbox.
less. To the point, like, what was it, last year where 2 years ago where Google produced AlphaGo, right, and beat people at Go, which was amazing. Yes. Yeah, no. So gravity is still a problem, and we can't connect that with quantum. So that's weird too. It works super well. I mean, we can do this whole thing with the two black holes, right? That's bananas. This is the Nobel Prize, right? It's two black holes hitting each other, sending like gravity waves out. 3 people got that. Of course, thousands of people worked on it, but you got to give it to someone because story. And I'm sure they're very bright. But it's just an absurd. So this is this giant feature in the universe of two black holes kind of going, and then it makes everything wobble a little bit. And Einstein gets another notch on the Einstein belt. Yeah, I don't know. I mean, we've come a long way. I mean, the equal sign was invented in 1500 or something like that. You know, it's weird, right? What? You know, so we're getting there. But it does seem that there may well be, and my story for this is really that, what they're putting in here are mostly differential equation type models, right? And that's what they got out for that thing. You can put algorithmic structures into this Eureka system. So Mike Schmidt actually left Cornell and created a company, Eureka, so it does all sorts of things. But there are things that are just fundamentally algorithmic, and that's so biology, social phenomena, all these things, and that's hard for physicists to understand. They don't like it, and maybe the details all horribly matter.
So you've got these maybe you want explainable models, but we in a sense already have that in mathematics, maybe like automated theorem provers.
Yeah.
Explanations that are generated are like just
Exhaustive searches, right?
Yep.
Right. Right. But it doesn't feel good though, right? Like at the end of it, you trust it, and you know it's done it, but there isn't a simple story. So, that's just the way it is. But I think it just is the way it is, eventually. But we have to eventually have this taxonomy of like, here's something we can explain and we can understand, like whatever it is, we can tell a story to each other and understand it and kind of go from A to B. But math is full of things where you're trying to prove something and there's this strange little, you have to hop over a log and then run along it, and then you have to swing over this thing and do not touch that bit or you will, right? And then you can get these odd little passages. And then someone later on maybe come along and was like, oh, actually you can do it this way. And this is a more intuitive thing. And that's always good. But often there can be these weird little, how did you do that? How did you find that path situation? So math sort of has it sitting around. Like idea, algebra, smash, truth, Usually we like to, if we can turn it into some graphical thing, then we're good. Now we've got a picture, good, that works. Anyway, this I think has held up pretty well, but it's interesting to see, this is 7 years now. So I got that wrong, it's 7 years now. and deep learning really hadn't quite taken off, but it started then in 2007. Okay, so we can't know everything. All right. I just want to mention a couple other things. So the self-organization is a term that you'll hear. We'll come back to that later on. But it's basically that there's some structures are emerging out of systems where there are many interactions, and there isn't some guiding thing. It's just a term that I wanted to throw up, right? So lots of things. And these are very physical kinds of situations, human stuff where we get global behavior from something like imitation, right? We're really good at imitating. We'll talk about that later. Okay, and how likely is complexification, right? This is a really, now we know there are exoplanets. We've got that story for us. We're able to measure how many there are and so on. We keep finding them. And this concern, like, are we alone in the universe? Like, how likely is it that, complexification, life is certainly part of that. I would say the advent of life is the advent of algorithms, actually, because you start to get algorithmic behavior and move away from raw physics. Loops and recursions and structures like that. But this remains a hugely open thing. So we're not going to talk about it. Now, you've used a few different things, but basically I just need to say that there isn't one universal approach to understanding systems. There are lots of classical kind of mathematical methods. Obviously we need everything from statistics. And then there are some pieces from statistical mechanics, which I'll talk about next, that really help in, say, networks and just thinking about this sort of emergence aspect, obviously machine learning. And then the computer modeling, which goes from everything where we're trying to model, disease spreading around the world based on incredibly refined data sets, and then the toy model type ones that tell us these stories that help us, all right? So we'll get to networks. That was a huge transition in understanding complex systems, the acknowledgement and the quantification of networks behind a lot of systems, and data. Data was the big deal. And that's the late 90s, really, for most of these things. Okay, smash that up. Okay, so this is what you want to get to in science. This is quite strange, but this was published in Science magazine. I like cats, obviously, but this was there's a really funny interview. If you want, you can click on this and find it. There's a couple of physicists who, they obviously don't work on cats in general, but one of them was watching his cat one morning drink some milk, and thought that lapping thing is kind of interesting, right? So, the point of this story is that if you've got a scientific theory working well, you have a theoretical model, which in this case is fluid mechanics. You have a simulating thing, which you can do with computers. And they also used a robot here. So they went next door to someone who had some robot they were going to put on the space station and said, can we use that for a little bit? We want to do something else with it. And they made a lapping machine. And so, what you're interested in there is how the amplitude of the lapping structure, the tongue, and the frequency, right? So you've got these things to dial. This is absurd, of course. And then you have real-world cats, right? So they actually went to YouTube and looked at lions and tigers. So they got some big cats and they got small cats. They had the cat and the... So fluid mechanics has had a great time for itself because, it ultimately was a pencil and paper science. You could derive the equations. But eventually computers came along and you could do the three things that you want, right? Simulate, theoretically explain, and empirically, right? Look at something experimentally. So it's a great, and as I said, got published in Science magazine. So it turns out that cats actually, they hit it with their tongue and it creates this little column. It's actually pretty interesting, right? So it creates a little column, surface tension keeps it together, and then they go chomp. So there's a slightly, it's a deft maneuver. Dogs just sort of like bash it up in the air with it, like they lap it. They just throw it up in the air and go, so also works, but not as, not the same. And apparently you shouldn't give cats milk. Cow milk, right? That's a no-no. It's in all the stories, but no. Okay. Okay, so here's the little robot they made, right? It's ridiculous. And then they have, this is massive cats, right? Cat, tiger, ocelot, lion, jaguar, unbelievable plot. And this is the frequency. So they found a scaling law for the frequency of lapping as a function of cat size. So this is like, your field is doing really well when you get out into the fringe a little bit, and now you're studying just like household objects with it. But pretty good. And they were able to predict the -1/6. There's their error, 0.1, so it should be 0.16, so that's pretty good. Anyway, weird, yeah. Bigger cats have lower lapping frequencies. Anyway, but this is emblematic and a really sort of silly example, but it's emblematic of what you want to get to. And the question is, can you move what you're trying to understand into these, get these three pieces together? And before you have lots of data and ability to do experiments, you just have theory, and theories flourish, right? So and physics did this. I mean, we have, go back a couple of thousand years ago, and you have all sorts of crazy ideas for why anything exists. We kind of still do, but data and experiments then eventually just get rid of your theory madness. But you'll see it; they flourish. Theories flourish, right? There's no more phlogiston; those things are gone, right? Once DNA became a thing, it's like, okay, we're going to do that. All right, statistical mechanics. Let's talk about this. So I'm going to give you this as a problem. This is a absolutely classic stat mech thing. So stat mech is this almost, it's an oxymoron, right? So mechanics, levers, things, pulleys, they all do very predictable things. You pull and you can figure it all out, and we have a whole field of work for that. But then statistical means like you've got jumbled probabilistic mechanics. That's very strange. But that was this great observation by Boltzmann, and I spoke about him in the manifesto, and a few others, Maxwell, that we can't know where everything is, but let's just imagine that kind of roughly, we'll give them distributions for their speeds and so on, and we'll just sort of smoosh it all together in the Boston ice cream making kind of way, of smooshing, and let it run. And they were able to, from those sort of assumptions about the micro behavior, statistical assumptions, derive the macro behavior. Things like the classic one would be PV equals nRT, right? The perfect gas, the ideal gas law. And then they thought about it, right? So, but there are lots of different kind of statistical mechanical things. There are magnets, for example, right? So the Ising model, which I'll mention, and I think I can show you a simulation, is an absurd toy model, right? It's just the idea that there are all these tiny little magnets, and that they want to be, just as real magnets like to line up with each other, we just imagine all these little ones trying to line up with each other, and that can, from that simple model, just on a lattice structure, we can actually do a pretty good job of predicting global behavior. So, but this is just a purely geometric one, which took a while to kind of emerge. It's sort of a big deal in the 80s, I think. Very 8-bit-ish sort of thing, but it's a very simple idea. And this actually goes into helping with understanding anything like porous media, right? So if you're trying to get oil out of the ground, which humans have been somewhat preoccupied with, then if you study percolation and porous media, then oil companies might give you large amounts of money. Things in biology, right? So there are pore spaces. So the idea is very simple. You say, let's have a funny little coin that has a probability of a space being open or closed. So this is like these black ones are blocks and the white ones are open. So you just realize it. You just say, oh, I want a lattice. So on a computer, you just make a matrix and then flip coins for each space. And this one, it's maybe more probabilistic that it's closed, right? So there's these are blockages. So if you're trying to run from one end to the other, you're not going to get very far, right? And you can't go across these corners. You can allow those sorts of things. You just run into, you could have wraparound conditions, but you wouldn't be able to get very far. So this one is not percolating. So in the great tradition of scientists talking about themselves, it's like coffee percolation, right? So this is, you say this one doesn't percolate. This one does, right? So there's a way to get from one end to the other. And of course, these are just little simple examples, but we think about bigger and bigger ones. You think about infinite limits and all these sorts of things. And you can imagine different lattices, right? Underlying lattices. You imagine in 3D. We'll get to the thing later on that the hexagonal lattice is the best 2D lattice. So so what we might do is say, a game to play with this is take this funny coin you have and dial it from 0 to 1, right? So with probability 0, you get an open space. So that means it's all black and closed off. And probability 1, we'll make another one, and it'll be all open, right? So you can easily go from one end to the other. So in between, there's going to be a transition, and it'll be a phase transition. It'll have all these qualities that a lot of physical systems do, even though it's purely geometric. There'll be a phase transition from where there is no global, what you can think about here is there is a macroscopic, globally connected set of white boxes that you can move around in. So we will get, if we imagine on a plot p equals 0, that's probably of a percolating pore, to 1, we'll get some plot like this, which will be the size of the largest component. And so that's that kind of phase transition structure we see over and over and over. It's a very important one. This could also, if we put this on a network and we imagine, these people here convey a disease or a story or a social contagion, right? Then we start to talk about disease spreading and spreading of whatever else you want, memes and things. Okay. So this is a sort of a raw example of a very, very big kind of set of models. Okay, so I'm going to just say these things. Aha. So here's the Ising model. And Ising was a graduate student in the 30s and just said, I'm going to make a funny little toy model of magnets. And this is the 1D version. You just have equally spaced, right? All these little tiny magnets, if you like, or they're little spins. And they can be in different directions. This is the 2D version on a square lattice. And so these ones are pointing down. And so you have some ambient temperature, and the warmer it is, the more these things jump around or don't care about what's next to them. And the colder it is, the more they're able to not jump away from their others, and the more they can be aligned to the spins next to them. And this is the kind of thing you get. This is the overall magnetism, which you can imagine then is just the fractional size of the largest component, right? Because it could become magnetic one way or the other. So out here, it's 0, right? So for high temperatures, it's 0, but as you cool this thing down, it starts to crystallize, the magnetism does, and you end up with going in one direction. Like so here, at 0 temperature, they're all pointing in one direction or the other. If you have an initial state here, then and just let it run, right? So you start off with some magnet, it's not fully magnetized, and the temperature is what it is. You just put it into a fridge, then it will drop here, it would go up here. So this is a classic kind of phase transition story. These are stable parts for the system. This is an unstable set of fixed points here, right? If it was truly balanced at 0, then maybe, but it's going to jump and leave. So these are the fruit flies of StatMech. And we'll come back to this later on. Right at this point here, so as you're going down here, you're starting to get little clumps of them join up, right? It's getting cooler. You're starting to get these little spins, a few of them, maybe 2 or 3 or 4 or 5, little groups of them connecting. And then right at this point, you get a power law size distribution of clumps, which is a very interesting thing, right? So you've got lots of little ones still, but you've started to get bigger ones and bigger ones and bigger ones. And then just as you go past that transition, the largest one accumulates the others and becomes this macroscopic one. It's only just visible from space, but boom, it starts to take off. So this, we'll get to this later on, self-organized criticality is this idea, which I think doesn't really hold up, but from the 80s that natural systems, lots of natural systems, somehow find themselves at this point. So self-organized means that it self-tunes, really, somehow it gets itself to this point. Because out here, you have some distribution of sizes of clumps of things that are little lattice animals that are pointing in one direction, but it's a very truncated distribution. Here, you've got one that's very large. You've just got one big blob. They're all pointing in the same direction, and then lots of other little ones that are pointing in that direction. So, but it's only here you get this power law size distribution. So it's very special. I could do this. I wonder if I can do this, get this to work. Yep. Nope. Oh, that was there the other day. No, it just died. Okay. Right. What's that? Yeah, that was that recently existed. I tested it just the other day. Okay, it's all right. It's no big deal. So these kinds of phase diagrams, you can start to build them for things like traffic and whatever. This is for right in these idea of critical points and these transitions between different macroscopic states. So this is temperature and pressure. This is for fluids. Right, so solids out here, so you can ice and water and steam, if you like. And this is something we've been able to do with lots of physical systems, but you can start to do it with other ones. This is a weird transition away from fluids. It's granular media, which has been studied pretty well now, but is still a difficult area because these things can behave like fluids, but not always, right? So these are actually just ball bearings. This is an old Faraday experiment, just a plate with ball bearings bouncing up and down. And Umbenhauer and so on were able to show that, in fact, you got these little things bouncing up and down by themselves, so little isolated waves, and they called them oscillons that just were disconnected. Anyway, they were able to sort of play around with this. You can do this with fluids, but it is a strange behavior of as I said, granular media. Granular media, incredibly important, right? Rice, wheats, there are tons of our foods are granular, and they give rise to, because of the way they move, it's not like a liquid, they're difficult things, right? They're difficult things to deal with. So silos, for example, lots of disasters have happened with things seeming like they're all stuck. They are stuck because you get these kind of force chain bridges at the bottom, and someone tries to like scoop it out and it all falls down. It's true that in silos, like if you just filled something up with water, again, the farming, you get these kind of what are called force chains of these grains, and they actually start to exert pressure on the sides, right? If this was just a liquid, the pressure would grow on the bottom as you filled it up. But these, you've got all these little sort of stacked on top of each other, and they tend to actually, and then they start to push. So you can fill this thing up with more and more grain. We'll come back to sand piles later on, and the thing can pop because you actually start to, it actually is pushing to the outside. They had some nice things. I know this seems very physics-ish. It is, but there's a square, so these are square patterns. They're able to see, sometimes you get hexagonal patterns. There's just a flat layer bumping up and down. And these were these oscillons in the wild. But you can do this with, say, traffic. There's a transition to where everything is stuck or flowing in certain kinds of ways. This is an example for biology, right? So this is a growing mold of some sort, and you get these qualitatively different patterns depending on what have we got, how much the nutrient supply and the wetness. So very standard kind of thing. So you may have systems where you want to be able to create so-called phase diagrams. So that's just an important thing to say. Doesn't mean you'll have to do it. And we actually, so you see these things for, say, pedestrian traffic. So crowds, right? What happened? Oh, yeah. 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 So they're basically doing that. Exactly, yeah. So Faraday did it in the 1800s and got all sorts of patterns out, and it was really sort of fun and, interesting. And this was to reproduce this famous experiment, but actually got these odd things coming out. Yeah, that's right. Well, in chaos, right? Did you do chaos? Yeah, there's a experiment with that at the end with speakers. I just want to say that this is a thing you may not be able to get. Well, let me mention this. So pedestrian traffic, depending on the density of people and constraints and so on, you can go from kind of panic states to orderly kind of movement. This is incredibly important for getting people out of, say, sporting stadium, if there are, or any arena where there are problems. How do you set up exit points so people can get out, right? People have really thought about this. So Mecca, the Hajj, right, that has changed over time because it used to be that you would simply you have to get stones from the mountains, and as I understand, and then come to these 3 pillars and throw the stones at them. So that just meant that you sort of had this 2D thing with all these people trying to get in to these spaces, and led to a lot of stampedes and many people dying in some cases. So they did a kind of fluid thing to start with, which was to take these pillars and make them more like airfoils. So they lengthened them essentially, like made them kind of have shapes so that people walk past them in a certain direction, and then added all of these walkways that were higher, right, so that people could come and move over the top. But you can see there are video cameras above some of these things, and you can, some of these pilgrimages, and you can, people have been able to see precursors before, a crowd really, falls apart and becomes a stampede. You can see these like little shutters in the pattern. You can see these little breaks. So in fact, you could actually say, institute something that said, everyone has to stop or whatever it is, because there you see these fractures that are starting to kind of move across the movement. Okay, so that's just phase diagrams, a big deal that may not be relevant, but it's a big piece. Okay. This is a surprising thing. So Ising, as I said, actually it was 1925, came up with this idea. They were able to completely solve their problem in 1D, just for little spins. 2D turns out to be really hard, and it was this fantastic work mathematically to get it done, again, just for the square lattice. 3D, unbelievably hard, right, to do analytically. And then 4D and up, it's simple. So this is a strange thing. A lot of systems are like this, where the 1D one is easy but not interesting. So it turns out the phase diagram for this one, it's a little problem for you. The phase transition happens when it doesn't really happen. It's at the limit. It's when everyone is pointing in the same direction, when probably 1, right? So if you have probably just away from 1, there's no global percolating cluster. So it's not at an interior point for the probability. This one you can solve. You can solve depending on the lattice and so on. Of course, you can simulate it well. 3D becomes hard to simulate, right? Right. Again, this is difficult to simulate. These things are harder to simulate, but actually analytically can be. So they're called upper and lower critical dimensions for systems. And often, once you get above a high enough dimension, it's basically like a random mixing thing. And the random mixing thing, or the mean field versions of problems, are easy to get at. So that's surprising. You would think it would just get worse and worse and worse. But actually, many problems, these are ones we've made up, right? Analytically, you can show that, for crazy things, like for dimensions 6.3 and above, which is insane, they're all easy and they're all the same. It's a good thing to know. Because you sort of think, 5 dimensions, that must be hard. But actually, 3 dimensions is really, really hard for a lot of problems, and it's really disappointing because we live in it. Okay. 2D is pretty good. We can show the pictures. Generally, we can simulate things, but it doesn't get us everything. So this is a nice little piece. It's just a stat mech, and I mentioned Maxwell and Boltzmann. Critical mass, Philip Ball talks about this, that they were actually motivated to think of their mechanics as being statistical by looking at what people were doing with people, right? So actuarial type studies or whatever, saying, so many people did this last year, and we're going to estimate this number again, and so on. Thinking about people statistically, which is weird, right? A lot of people have belief in fate and God and so on. So it's sort of not great to say, on average, we think this many, this number of people will be kicked to death by a donkey this year. That's kind of weird. So anyway, right, analytic approaches. As I said, algorithms. As algorithms become more and more important in your system, the degree to which you can write down some mathematical model that explains it all will fall away, and that's fine. And this transition to simulations, being able to do so much more for us, is huge. But at some point, we need to be able to really draw a line and say, look, this is just something we cannot do mathematically, and I don't think we're quite there yet. We have some of this stuff with Gödel's theorem, but no general theory, complexity, right? These things are actually pretty well defined, though. The complex systems are everywhere. This is just sort of, say this again, I want to mention universality again, which means that, not always, there are many systems that actually have the same global behavior, and that makes this sort of world of thinking about things, complex systems sort of possible, like starting to talk about across systems, especially something like robustness, which we'll get to next. Big deal. you can think about robustness of ecological systems and organizations and actually have informative things to transfer. Okay, and as we said from the manifesto, we're actually working on complex systems because we can, right? We have the tools to do it. Okay, so that's where I wanted to stop. I thought maybe, I've got a few more minutes, I thought maybe a good point here. Okay, so in an assignment question you'll have to play around with some percolation stuff. It's good, it's very nutritious. It's good for you to do that, yeah. And I'm worried about your nutrition. Okay, so I'm gonna go to this one here, let's see. If you just give me a second, I will find this. I know it's here. It's been tweeting a lot. Who does this? Me. Okay. Oh, okay. So I meant to show you this the other day. Maybe I did. This is the graph of this extraordinary visualization. This is back to 1966, which is UT Austin. This is back to shootings. So the blue line coming down, I know it's a little hard to see, is the number injured, and the red line is the number killed. So that's going on. If you go back in time, right, there are more events like this, but this is just where they started. And this blue line is actually part of the graph. And this is just an unbelievable, it looks like it's a divider, right? But this is an estimate of the number injured in Las Vegas. This is just ridiculous. And the red line, I mean, it's the worst ever. It sort of, unfortunately, comports with what's come before, but this is incredible graph. I don't know what to say. But anyway, okay. Let me try to find. Yeah, it was this actually. I don't know if this has if this has weird. Maybe it just has music. Okay. So it's about whoops. This is a robustness thing or a change of systems. It's a little over the top, but what's being reintroduced into Yellowstone in that area. So it's just words, right? It's just words. So, excitement. Okay, just it makes me not want to do it. Right. Okay. So, I don't know the extent of what that's really all true. Like how much that claim, the thickening and all these sorts of things. But I don't think this was predicted quite to that degree, right? I mean, it's like let's get some wolves back. They should be wolves. Yeah. But having an understanding of systems such that you could actually really kind of map that out and simulate things is really, obviously, unbelievably powerful. Being able to convince someone that this is how it would go, predictably, that's even more impressive. But I can only imagine the sort of narratives for bringing wolves back were not this, right? Because that seems an unlikely event. It's just like, wolves are cool, we should have them to eat things. And that would sell better. But this is that seems like a pretty remarkable thing. Okay, so we're going to talk about robustness next Tuesday. And okay, I will communicate other things with tweets and instructions. All right. I wonder if that's true.